The main issue is probably just if it gets directly in my face via air, via touching the plant or via touching a dog.
Crazy. You know that as a kid?
Oh, yeah.
So
Pollen's
you
all-
didn't have like a nice, like, running outside
I
childhood?
definitely played outside as a kid, just probably less so in the spring because pollen and I was terrified of bees.
I used to grab bees until they started stinging me, But I was pretty good, so they wouldn't sting me. But,
My thing was catching lizards.
Oh, probably. Did you ever put them on your hair, them back in?
No, didn't think to do that.
It's pretty fun.
Just like catching them. I was the family lizard catcher at one government house.
yeah, they made me do that too. I also like spiders.
No, I'm an arachnophobe.
Yeah, you did say that.
I did? Okay.
Like, I guess I don't, like, do you think it's like, didn't kill you, or like, why are people scared of spiders, Like, I guess I don't.
It's the same kind of thing as people who would look at a very small, non-venomous, bug-eating snake and still scream and run to the other side of the room. It's not about logic. It's something buried deep in my lizard brain that just hates what I'm seeing. I think this is where we were yesterday. So, uh, 3 seconds on the hour. Any questions or needs from you guys before we resume today?
Wait, why is it negative word?
Because if we're looking at the case of this particular proton, and it goes from the positive end to the negative end, its potential is going to drop, which means that delta P would end up being negative, which would then invert the other side to make it positive. So when the E field does positive work on the particle to move it from one side to the other and to change its potential into kinetic, that work is positive, but the change in potential would be negative. So personally, I would not write it this way, but the book does. So we left off here yesterday looking at the energy interactions that go on inside of a capacitor. As a particle travels from one side to the other, it's going to transform its potential energy, and all objects in fields have some amount of potential. That potential is going to become kinetic as it accelerates towards the other side. And we've been able to compare the change in energy, the change in potential to work done by the field, because the field is exerting a force as the particle moves some distance. So you can't escape the work equation either. And this is the main piece that I think you guys should care most about, right? Well, I suppose that these two lines are basically the same thing. But this is the actual equation for change in energy, change in potential energy inside of an E-field. But before we move on, I'm going to add an additional formula, less to do with electricity specifically, more of an energy generalization. If there's, this is not going to be a 100% accurate thing all of the time if we're looking at every single energy example in the universe, but for all of these particle acceleration type questions, generally speaking, if PE is going to drop, that means KE is going to rise. So at least for the purposes of these questions, this rule should hold true. I will let you know if it's a case where it does not. So with that said, math time. Good morning. We have a capacitor here, and the E field inside of this capacitor is a nice even 25 newtons per coulomb. And the two plates of this capacitor are 0.01 millimeters apart. So this is the physical capacitor that we have right now. And the first thing we're asked is, we're going to, I'm using a pair of cosmic tweezers, just take a proton and drop it right here in the middle. It didn't start on the other side and move there. We're putting it right here, so this is going to be its starting point. With that as its starting point, we are asked to find first, and we'll focus on this part first, the particles of final kinetic energy. Before we do anything else, this is just a logic question and not a trick question. What is this proton going to do now that it's in the Z field?
Right.
It's going to move to the right. It wants to move away from the positive plate and move towards the negative plate. So it's going to move from left to right. Since we put it right here, it's just going to move from this spot the rest of the way across. So it has that much space to accelerate. So we know its starting location within the field, we know the field strength, and we know that it is a proton. Since it's a proton, we know a couple things about it automatically, such as its charge and its mass. So, for our first question, where should we begin? Very good. So, we put the proton halfway between the plates, which means it's only going to move half of this distance between them. So half of 0.01 millimeters would be 0.005 millimeters. That is the distance it is going to move. So we do know that now. So to find the change in the kinetic energy of the particle, we need to find the change in potential energy of the particle. So I'll back up just a slide so you can remember that formula, which I will write down. It's not on the next slide. And I recommend going ahead and combining that formula with this one. So we have positive PE in that formula. Positive PE would equal negative delta KE. So I'm going to rewrite that as negative delta KE equals negative QE delta X. And those negatives are just going to cancel.
We now know everything else, so.
Yes, we know particle charge, we know E field strength, and we know how far it's going to move. For some reason, my delta looks more like a crescent moon here.
We have to convert our distance. 1,000, right?
Converting this to meters is going to make it 1,000 times smaller.
Wait.
Yes.
Yes.
Smaller.
Oh, that's really small.
Yes, capacitors are very, very tiny. And all of this is somehow jammed inside of this tiny little tin can. This is not on scale, they're actually like this big. So Q, abbreviate that slightly, 1.6 times 10 to the negative 19, times our E field times our delta X. This is 5 times 10 to the negative 3, so I think it should be 5 times 10 to the negative 6 meters. And that will give us an answer, which is going to be very, very tiny, because this is the energy of one teeny tiny mass moving a teeny tiny distance and tied up a teeny tiny capacitor. So this number is going to be small, don't worry.
Is it in joules?
Correct. This is energy. We are looking at energy, change in energy as we travel, so the answer will be in joules.
I got 2 times 10 to the negative 23.
Very good. Does anyone disagree? All right. So that is the change in kinetic energy. Not a trick question. If we just drop this proton right here with our cosmic tweezers, what would its initial kinetic energy have been?
0.
0. If we're just holding it in place there, it's not moving until we let it go and the E field starts doing its thing. So delta is always final minus initial, but we know the initial was 0, so the final kinetic energy will be the same number. Now that we have kinetic energy, we just should ask ourselves how we can use that to find velocity. I'm also going to ask myself why all my deltas look like chunky moons today.
I don't look as bad as the one with the second one, but
Okay.
that one definitely does look like a half moon.
So K equals 1/2 mv squared.
Very good. That's just the old formula for KE, which you will also never escape. We now know what the final KE of the particle is, and we know its mass because it's a proton, so we just need to algebra our liquid B. This number will also be very small. Right now, sorry, I got my notes backwards. This one won't be as small.
I got 154.8.
Very good. Does anyone disagree? I'm just gonna wrap it a little bit.
Okay, I have a question.
Answer, yes, answer.
Okay, so if you were given acceleration instead of electric field, did you have to put in F equals MA to find, or do F equals MA to find the force and then plug that in into the work formula and then put that in as the delta P?
Yes.
And then change that to kinetic?
Yes, you could have. That would have ultimately amounted to the same math. And we know this because E field is equal to force times charge, force divided by charge. So that means E field times charge should equal force, and that's just force times distance.
Yeah, which is, okay, yeah.
So, good. That's good pattern recognition. It's all connected. Everything is application of the last thing. All right, so that's the first two questions answered. Not a whole lot of energy involved, but this one electron is actually going to move pretty fast. So electricity, when properly motivated, is very, very quick. That said, this is just one electron moving through the one object, presumably by itself. So in an actual current system, things will likely move much slower than this. But properly motivated, such as lightning bolts, single electrons can move very fast. So those are both very good answers. Next, one extra little concept question. This has all been assuming that the particle we drop in here is a proton. If instead of dropping in a proton, we dropped in an electron, and we put it right there, what would be different?
Anything that was put right there?
Yes, instead of dropping it in the middle, we're dropping an electron there. What the slide is officially asking is, what is this particle's potential right here?
Zero?
Yeah, sorry, artistic license, I'm assuming that this is as far as it goes. So if there's no more room for it to travel, it's where it wants to be, it doesn't have any potential. This is the electrical equivalent of an object sitting on a surface having 0 GBE compared to that surface. It is where it wants to be, and the electric field's not going to push it any further, because the electrons are going to do the opposite of whatever the protons do. On the other hand, looking back at the proton, let me ask you, what would this particle's potential be at this particular spot?
Wait, can you ask that again?
When we dropped this proton right here, what was its potential energy before it then started accelerating to the other side?
Yeah, negative.
It would actually be positive. Good question. Because we'd be comparing potential energy initial to kinetic energy final. So in this position, the proton had a positive amount of potential.
Oh.
As it moved over, that potential dropped as KE went up. So in this spot, the potential was the biggest, highest, most positive number it was for that particular proton. By the time it reached the other side, it didn't have any potential left, like how the electron has no potential up against the positive plate. It is where it wants to be, it's not going to go any further. Any questions?
The electron will push the against the negative plate. It's just the same process backwards.
Correct.
But because distance is delta x, would it have like the same kinetic energy as putting in a proton pushed up against, what was my first example? Okay, like if you have, okay, keep that electron there, right?
Uh-huh.
Yes, and then add a proton, but on the, against the other plane,
Okay.
right? Do they have the same kinetic energy?
So put a proton here.
Yeah, like, because,
If they start
oh,
from,
their charge is negative, wait. Okay, sorry, continue.
if these two particles were both placed here, they would both have zero potential. If both of these particles,
Oh, I meant reverse, yeah, I'm sorry.
yes, if we reverse this, and they both started on the side they don't want to be on, then they would still have the same amount of potential. It's just going to be the same big number that will turn into kinetic as they rocket across to the other side.
But it's equal to each other,
Yes,
even though they're going different directions.
correct.
Which means that it's not a vector then?
It is a vector, but the charge direction factors into it.
So positive.
So, hang on, let me label all the vectors in here. E field direction is a vector, X is a vector. Charge is not technically a vector, although it is positive or negative, and that will affect the ultimate direction of the vector. So it's like a half vector. That said, energy, okay, you know what, energy isn't a vector. So it can be positive or negative, like Q, without either of them being vectors. So we've got two vectors and two not vectors.
Wait, can you help me go through the math to see why the two potential energies would equal each other? Like, okay, so for the proton, the charge is positive, right?
Yes, yes it is.
So they have the same force and they have the same distance. So it's a negative delta P, right?
Mm.
Whatever, like, let's say negative X.
Yeah, okay, yes, if the proton starts here and goes over,
Yeah.
that would be a negative.
Okay, so then let's do the electron. So the electron has a negative charge, so that would turn positive. Force, I mean, the E field is the same and the distance is the same, so isn't that now a positive delta PE?
The magnitude of the distance is the same, but it's moving in the opposite direction.
Oh, so you do have, like, for the
That's
electron,
why,
it would be
yeah,
negative.
that's why I specified this as a vector. The direction it moves in does matter. How do you guys feel about this? I know that out of probably all the things we talked about, the electrical stuff is more just talking because it's hard for me to show you any of this given how small the particles are. In fact, I just can't electrocute things in here.
For the electron to move over to the positive plate, would it require like more force or something if it's not moving in the direction of the E field? Like, would it be easier for the proton to move since it's in the direction?
It wouldn't actually make a difference. The arrows always have represented the direction a proton will move. An electron moves as easily, it just does it in the opposite direction.
Okay.
And I know why it's like this now. It's all thanks to Benjamin Franklin. Okay, maybe not all thanks to Benjamin Franklin, but it's at least partially thanks to him, because he is apparently the person who did the experiments that differentiated between protons and electrons, and he just arbitrarily decided all the ones over here are the positive ones forever, and we're noting things based on that. All the ones over here are the negative ones forever. So the differentiation there is at least partially his fault. And because we just took those notes and ran with them, everything is always written and the arrows are drawn from the proton's perspective. The field moving this way just tells us protons go this way. Electrons will move as easily, just opposite direction. They're anti-backwards particles. Okay. So I'm going to jump ahead just a tiny bit because there's actually more than one way that the little can capacitors that I drew over there that I have in the lab tables are built. And I forgot that they could be built like this, so I wanted to mention it before we move too far on. You can make a capacitor by taking the two sheets and rolling them up into a tube and then encasing that in plastic. But some of them instead are made with a series of plates running end to end, kind of creating a stack of capacitors that will ultimately have its own net capacitance, and that's the capacitance of the total object.
For touching each other?
The plates themselves aren't touching each other, but each plate is touching one end of the capacitor so that it'll be positive or negative. So like all of these plates are connected to one of those metal legs so that it's connected to one end of the current. All the other plates are connected to the other leg so that it gets the opposite charge. So they aren't all rolled up in there. Sometimes they're in this organization as well. I forgot they were built like this, so I wanted to mention it. Okay. We've been throwing the word potential around. And there's a specific way that we tend to note potential when it comes to electricity. And it's using a measurement that you have definitely heard of and interacted with before. It's called voltage. We don't really have a good gravitational equivalent to voltage. Because gravity, we just have the potential energy from the field, and we just take it at that. But for electricity, because we need a good kind of standardized unit for all of our battery sizes, we came up with the concept of voltage. And voltage represents the potential of an entire circuit, kind of separated from the potential of single charges. In this formula up here, and in terms of the math we're going to actually do, we mostly only care about the beginning and the end. The middle is just to show where it comes from. But within the middle, we can see that the voltage is defined as the change in potential of a particle as it moves through an E field divided by that particle's charge. This term contains a Q in it, so we're basically just dividing the Q out. So this voltage is now independent of whatever charges are moving through the system. It is now just a definition of the potential field of the system itself. completely separate from whatever protons or electrons end up inside of it. Yes?
Can you repeat what it's independent of? I'm sorry.
It is independent of the charges moving through it. We have divided out all of the Q's basically. From beginning to end, it's just voltage equals E field times distance moved in the E field.
Thank you.
You're welcome. So the voltage is going to be a standard measurement of what a circuit or a component or a region of space is capable of, regardless of what actually walks into it. And the funny thing, I know this says delta V, but this is actually just the standard measurement of voltage. Because voltage represents potential, potential needs to change from one place to another for anything to actually happen. So even though I'm going to write down formulas that just have V in it, it always technically implies delta V. Because for anything to change from one place to another, potential has to change between those two zones. When objects fall, they're going from high potential to low potential. When the protons move through the capacitor, they're moving from high potential to low potential. Potential always has to be changing for the object moving through the field in question. So delta V is actually the standard here. It's kind of the only way you can measure it. Yes?
So we have, like, would you ever give us one that has initial and final voltage? Or most of the time will it just be?
Kind of. This is skipping ahead a little bit.
Sorry.
No, it's okay. It's a good question. It's one I haven't thought about being asked, so I'm glad you did. This is a circuit diagram. It's slightly different from the ones we've done in lab this week because these are resistors instead of capacitors. But I'm using resistors in series because let's say that these are all the same size. So they're all the same size of R. And I'm going to make this a 3-volt battery. So this battery has a voltage of 3. That means that the difference in potential between one side of that battery and the other side of that battery is equal to 3 volts. This kind of speaks to its ability to push things through the circuit. The more voltage you connect to a circuit, the more potential difference there is from one side to the other, the more it's going to push things through it. This is, again, it's kind of hard to compare this to gravity anymore, so I'm going to start comparing these things to water, which would make voltage like the water pressure. The more you crank up the pressure, the harder and faster it's able to push things through the system. So, higher the voltage battery, the faster things move through the circuit. Every single battery, and I'll draw in a kind of double A shape here. Every battery has one end with a higher positive potential and one end with a lower, probably 0 potential. And when the battery is disconnected, nothing's going to happen because there's no connection between the two sides. But when you take one wire from one end to the other, now there's a connection and electrons will flow from high potential, technically, current will flow from high potential to low potential. And it just has to go through the circuit to do that. And technically speaking, in series, when current has to push its way through a resistor, it eats up some of the voltage. The potential drops across the resistor. Imagine like a kink in the water hose. You go outside, you turn on the water pressure, but there's a knot in the hose. The water might be really fast and there might be really high water pressure leading up to that, but the water has to burn off a lot of its pressure and energy to force itself through that kink and ends up being slower afterwards. These resistors in a circuit accomplish the same thing. It forces the system to diminish its potential in order to get the current through there. So the potential from one side to the other has dropped. It's going to drop again across the second one. Why does my one look like that? And it'll drop again across the third one.
You can end up with zero? Or you want to end up with zero?
By the end of a circuit, you end up with 0 volts.
Then what
Or
powered
rather,
it to keep going?
it's 0 volts compared to the other side. Like if you have a 3-volt battery, the voltage will be 3 less on one side than the other. Right.
Then I don't get how like the charges tie into the voltage.
They don't. The voltage defines the pathway that the charges will follow. But you can have voltage and no charges moving through it. Voltage, we divided charge out. Voltage can exist without a charge moving through it. Voltage is the pathway that charges can then follow.
But does nothing happen if you have a voltage with no charges?
Yes, you can have a voltage and no current. A good example of this would be if you just, here's my calculator. Thank you. Well, use mine because I know where the batteries are. I can just pull them out. But thank you so much. I appreciate that. This right now is voltage with no current. There is a voltage difference on both sides of this battery, but because the resistance of the air is too high for current to travel through, there's just no current right now. But if I connected both sides with something more conductive, like a metal wire, the current can then more freely flow. And it always flows from high potential to low potential. And
Wait, so you said, I'm sorry.
I might be making an assumption about your original question, but even though this is now 0 potential, the inside of the battery is even lower potential. The current still wants to go back into the battery, even at this point.
Wait, so you said that voltage makes a pathway for the charges to flow through?
It defines the path they will follow,
Okay.
because they always go from high potential and high voltage to low potential and low voltage. And so to apply this to the math on screen here, the change in voltage from one side of the battery to the other is going to be 3 volts. That means there's an E field throughout the entire circuit. Whenever you connect up a circuit, you're basically just sending an E field through the wire to the other side. And that will change based on the distance traveled through the circuit. This is technically a new unit, so I'm going to do that. Trying to define all the variables. So, officially for the notes, delta V represents voltage. It's specifically defined as change in electrical potential always measured as a difference in potential between two zones. And probably for the first time in physics class history, the unit makes sense. Because voltage is measured in volts. Which is also abbreviated to capital V. So the unit and the variable are the same letter for the first time in probably ever. Sorry, funny bone.
So is that why basically, like, it's delta V, because even though, like, you said it was basically V, because at the end it's gonna be 0, like, you know what I'm saying? So then, like, it's just gonna be the same.
Oh, wait.
The
Yeah.
delta V across the whole circuit is the same, like, is gonna be 3 volts.
Right,
So we
because
just
it's
say it's a 3-volt battery.
Okay.
Wait, but is that the right logic? That is because you end up with 0 and then you start again with the 3, so you never really had like,
So
you
that's
didn't
why
end
it's
with 1,
delta.
so it's not now a 2-volt.
Correct.
Okay.
Yeah.
There would be some point in the circuit where the voltage is presently equivalent to about 2, but it's then going to drop across the next resistor and drop across the next resistor, and it'll always be 0 again before the end of the battery.
So that's why it's considered like delta V.
Yeah, it's for the entire circuit. It defines the entire pathway. I believe this is the handiwork of one physicist named Alejandro Volta. All these electrical terms come from people's names, and so their names just end up sounding that much more metal because of it. This next piece, you don't need to write this down. This is just trying to make a comparison to gravity. If there isn't a good one, like there is no real defined gravitational equivalence to voltage, but you could do the math for one. And so that, if that existed, it would be 9.81 times the change in height. That would be the difference in potential between where you started and where you fell to. Not needed for this class though. Hold on. Sample's missing something. Okay, there's a flaw in my notes, so I need to revise those. I apologize. I wanted to end on a sample question. I don't have one ready. So instead, I'm going to give you one more formula that will be useful for your homework as you begin it over the weekend. It's not going to be due till Tuesday after next. I do recommend you start it though. The sooner you start, the sooner, the easier it is to finish, in my opinion. Okay, I'll be consistent, delta V. So, when you plug a capacitor into a circuit, you are putting it into a system that has a voltage. So, the function of a capacitor is to hold charge within itself. And this formula tells us how much it can hold based on its physical situation. C is the capacitance of the capacitor. Capacitance is equal to the maximum charge it can presently hold divided by the voltage of the system it's in. Which means one capacitor can hold different levels of charge depending on what type of circuit it's plugged into.
Why does more voltage mean less capacitance?
That's a good question. It's, well, like the physical capacitor will have the same C. So ultimately, if this is being held constant, increasing V would actually increase Q. If C was constant, so let's just say everything here equals 1. 1 equals 1 over 1.
Okay.
If, hypothetically, capacitance was constant and we doubled the voltage, what would Q have to be?
No,
Right. So for the same capacitor, doubling the voltage will also double the charge. So it's just a matter of what is held constant. It's Friday, and I don't want to hold you over on the weekend. So start your homework, send me any questions you have, but as the final reminder, no class on Tuesday and no lessons. So I know it's probably not a vacation because of assessment day, but enjoy not having to worry about it. Okay, so I either don't remember assessment day when I was a student, or it wasn't a thing at the time. What is happening exactly? Because I don't have anything that day.
There's two different types, like one's the survey and one's like actually answering different types of questions, like what you learn. Which is kind of difficult because they all learn different.
it like validates the PC, education. I think that's what I was explaining.
I don't know, but mine's at 8:30 in person, I'm kind of salty.
Ooh.